Hi, everybody. And so I just wanted to record a quick video giving some more examples of those three different methods of limiting reactant problems that we talked about in lecture today. And so in order to do this, I'm going to go ahead and run through one of your homework problems for this week. So this is from homework 5, number 22. And if you're actually watching, if I hold on to this video and you're watching this in the future, it might not still be number 22, but this might still be one of your homework problems. But in the fall semester 2021, this is homework 5, number 22. And so in this question, we're given the amount of iron 3 oxide that we have, and we're provided with our amount of carbon monoxide that we have. And we're asked to figure out the maximum amount of grams of iron that can be formed. And so like we talked about in lecture, there are 3 basic methods that we have, at least that I've talked about, in order to solve limiting reactant problems. In the first of those methods, what we do is we simply go through the whole entire stoichiometry process and determine how much of the product we can actually make based upon both reactants. And so we run through the process twice. And so let's just recopy out our equation here. Fe2O3 plus 3CO, and I'm just leaving off the states of matter. We are given 33.4 grams that we start with of Fe2O3. Actually, instead of writing it there, I'm going to write this up at the top so that I can hopefully leave it right there. So 33.4 grams. 47.2 grams, and we're looking for our grams of iron, looking for our grams of Fe. And so in the first method, all we're going to do is we're going to run through the problem once with our starting amount of iron 3 oxide, and see how much iron we get, and then we're going to run through the problem again with our starting amount of carbon monoxide, and see how much iron that we get. And so we have our 33.4 grams of Fe2O3. We use our molar mass of iron oxide. Which I don't remember if it was supplied in the problem or not. It wasn't, so you would just have to calculate the molar mass of iron 3 oxide, which is 159.69. And so here we've gone from our grams of Fe2O3 to moles of Fe2O3. Next, we're going to use our balanced chemical equation to now go to moles of Fe. And so we can see from our balanced equation here, we have 1 iron 3 oxide to every 2 moles of iron. So we're going to have to put our moles of Fe2O3 down bottom so that cancels out to 2 moles of iron. And then finally, use our molar mass of iron. And we do all of this out, and we find that this 33.4 grams of iron 3 oxide is going to produce 23.3 grams of iron. Next, we run through the exact same process, but we're going to go ahead and start with our starting amount of our carbon monoxide. And so our 47.2 grams of CO. And so the only difference in our pathway here is that we're starting with grams of CO to moles of CO, but then we're going to go to moles of Fe, and then finally to grams of Fe. So the same exact process, just with our different starting material. 47.2 grams of CO, the molar mass of CO is 1 mole per 28 grams of CO. And then again, we use our balanced chemical equation, and we see now that we have 3 moles of CO to every 2 moles of Fe. And then finally, our conversion to grams of iron. We do this out, and we see that this amount of carbon monoxide can actually produce 62.8 grams of Fe. And so when you do problems out in this way, now you just recognize that the absolute most iron oxide we can make is our 23.3 grams, because that's as much as we can make based on our starting amount of our iron 3 oxide. And so this then tells us that the Fe2O3 is our limiting reagent, and that 23.3 grams of iron are actually formed. And so that's our first method. Again, simply running through the whole entire process for both reactants. Whichever one creates the least, that one's our limiting reactant, and that's how much of the product we'll be able to make. Our next method is what I call the mole ratio method. Let's go ahead and just erase, maybe, there we go. So erase what we've done here. Insert maybe the Jeopardy theme song as I'm doing this. Just takes a little bit of time. Okay, so in this mole ratio method, what we're going to do is we're first going to convert our given amounts over to moles. And so we have our 33.4 grams of Fe2O3 so we're starting with 0.209 moles of our iron 3 oxide. Do the same thing with our carbon monoxide, 47.2 grams. And we can see that we're starting with 1.69 grams of the carbon monoxide. Now we set up some ratios. And what I typically do is in this method, you always divide one by the other. I usually divide the larger by the smaller, just so I end up with a 1 down bottom, so to speak. And so I'm going to divide my 1.69 grams of CO by my 0.209, or sorry, not grams of CO, moles of CO, by my 0.209 moles of Fe2O3. And I divide that through, and I see that I have 8 moles of CO to every 1 mole of Fe2O3. Now remember what this is this is how much I actually have. That's how much I have according to my starting materials. I have 8 moles of carbon monoxide per every 1 mole of Fe2O3. Now I'm going to go ahead and compare that to what I actually need. We look at our balanced chemical equation, and we can see that we need 3 moles of CO to every 1 mole of Fe2O3. And so that is what we actually need. And since 8, what we have, is larger than 3, what we need, that tells us that we have more than enough of our carbon monoxide. We have plenty of carbon monoxide. We have 8 moles of that for every 1 mole of Fe2O3. We only need 3. And so the carbon monoxide is absolutely in excess. We have more than enough of it. And so that once again tells us that our Fe2O3 is limited. And so from there, you would then take the last step. Let's go ahead and just erase most of this now. So we know that our Fe2O3 is limiting based on our mole ratio amounts. And so we're going to go ahead and just base the rest of our answer off that. And so we know that we're starting with 0.209 moles of Fe2O3. And so then we go through the same process. Now we're starting with moles, and so we're going to use our molar ratio of our 1 mole of Fe2O3 to 2 moles of Fe, then 55.85 grams of Fe to every 1 mole of Fe. And sure enough, that once again gets us to 23.3 grams of Fe. Now, both of these methods, the sort of do it all out and the mole ratio method, are fantastic methods for what they are, which is namely that you can easily find the amount of product based on both reactants by determining the limiting reactant and going from there. It's not as easy using those methods, though, to find the amounts of the other reactants involved, which is sometimes required, or maybe the amounts of other products. And so that's where I also really like what we call the Bcaa table that Chem 101 uses. And so let's take a look at how you would work with this table, and you'll also see how to set things up within the Chem 101 platform. So the way that these Bcaa tables work, so it's before, change, and after. So you're going to put your starting amount in moles along this first row here. And so just the same way that we did before, we're going to convert our amount of iron 3 oxide over to moles. And so our 33.4 grams, you've seen this a couple of times now, then divided by our molar mass of the 159.69. And as we saw in the last one, that's our 0.209209 moles of our iron 3 oxide. And the same for the CO. We already did it in the last problem, so I'm not going to work that one out again. But our CO, if you remember, was 1.69 moles of carbon monoxide. And so we're going to go ahead and put those in. And we can see that we're given those. Those are a couple of our options. So that's good. There's our 0.209 for our iron oxide, our 1.69 for our carbon monoxide. And we're starting with 0 and 0 for our products. And so the next step in these Bcaa tables is now we basically just choose one of the reactants and run with the problem as if that were our limiting reactant. And we'll be able to see if we were right or not. And so I'm going to go ahead and just say that I think that carbon monoxide is a limiting reactant. So again, pretending that I haven't seen what we've already done. And so we know that if carbon monoxide is our limiting reactant, then all of that will be used up in the reaction, meaning our after amount, our final amount of carbon monoxide is going to be 0, which means that it had to have decreased by 1.69 moles. So we had to have had a negative 1.69 there. And so let's take a look at what that means for our amount of the iron 3 oxide that had to have been used. And so if we used up 1.69 moles of our carbon monoxide, we look at our molar ratio from our balanced equation. We have 3 moles of carbon monoxide to every 1 mole of Fe2O3. And we do this, and then this works out to a change of 0.56 moles of Fe2O3. Now, for one thing, we can see that's not even an option in our table that Chem 101 gives us, so we know that's a problem. But let's just take a quick look as if that were one of the options. And so let's go ahead and actually go ahead and erase this, but we're going to remember that number, our 0.56. And let's just set up our own table real quick here. So here's our before, our change, and our after. We had 0.209, 1.69, 0 and 0, minus our 1.69. And we just did our math to find out that that meant that the change of the iron 3 oxide would have to be a change of 0.56. And so now, if we then went to fill in the after, we can do 0.209 minus 0.56 would give us a negative 0.351 moles of iron 3 oxide. And we can't have that. That tells us that this reaction would have had to have used more iron 3 oxide than what we actually started with. So we know that must be incorrect. And so that tells us immediately that we had chosen to go with carbon monoxide as our limiting reactant, but that was wrong. It means that iron 3 oxide is definitely our limiting reactant. And so we're going to go ahead and just get rid of this and get rid of this. We know that iron 3 oxide is our limiting reactant. So that's going to be a 0 there. That's going to all be used up. We're going to use 0.209 moles of it. And so then we can figure out how much of the carbon monoxide has to be used. So 0.209 moles of Fe2O3, 3 moles of CO for every 1 mole of Fe2O3 gives us a change of we're losing 0.627. That's our change of carbon monoxide. And then we can fill the rest out. 1.69 minus 0.627 means we're going to be left with, there it is, 1.06 moles of carbon monoxide. But we can also fill out these other two. So again, based on our limiting reactant, we're going to use 0.209 moles of Fe2O3. For every 1 mole of Fe2O3 used, we form 2 moles of iron. So 0.209 times 2 is going to be change of 0.418 for our iron. For every 1 Fe2O3 used, we form 3 CO2s. So 0.209 times 3 is a 0.627. 0 plus 0.418 means that we're going to have 0.418 moles of iron and 0.627 moles of carbon dioxide. And so this is very useful then if we have a problem where we want to know all of this. We might want to know how much of our excess reactant is left over. We might want to know the other product. And we're almost there now for all of that. You see, all because we're sitting here with moles now. So we just have to use the molar mass. We would then convert all those to grams, and we would have all the information we're looking for. And let's just make sure that this one does work out. And so we have our 0.418 moles of iron that we said we formed at the end, multiplied by iron's molar mass, the 55.85, and sure enough, we get 23.3 grams of our iron 3 oxide, or sorry, grams of our iron. And so that would be our final answer. And so those are your 3 basic methods. And like I said earlier, there are a lot of other methods that are out there. These are just the 3 that I sort of find most useful and easiest to work with. But if you find some other methods out there, absolutely go with those. As long as they work, that is fine. But I hope this has helped. And if you have any questions, be sure to come see me and we can talk about it. Thank you.